So in single variable calculus, you develop techniques not only to compute derivatives using various rules of algebraic formula manipulation, but you also developed some other tools for at least estimating derivatives based on the graphs of functions and also based on tables of data. And so the last couple things I want to mention here are that we can still do that same kind of work for partial derivatives that we did for ordinary derivatives in single variable calculus. So if I have a table of data points for a multivariable function, like this one, which relates the ambient air temperature and wind velocity to the observed wind chill reading. I mean, right now we're in the middle of summer, and so wind chill is maybe the last thing from our minds, but another 6 months from now, you might look up a table like this. And so we can compute partial derivatives from this just by, again, taking a trace, just by taking either a single row or a single column of this table, depending on which one of the variables that we want to hold constant. So just as an example, if I want to find the v partial derivative or estimate the value of the v partial derivative based on this table, then what I would want to do is I would want to hold t constant. But holding t constant means that I would want to focus just on a single column in this table, right? So if I want to know the v partial derivative at 20 comma minus 10, so if it's negative 10 degrees outside and there's a 20-mile-an-hour wind, I want to know how does the wind chill change as a function of the velocity. So to find that, I would let the velocity vary, but I would want to keep the temperature constant. So I would just look at this column of numbers, and I would get a single variable function, and I can use the slope of a line in between two of those points to estimate this instantaneous rate of change at a given point. Same thing to estimate the t partial derivative. I would want to let v be constant, and so I would look at a single row of this data rather than a single column of this data. So that's the main idea behind interpreting first order partial derivatives off of a data table. We can also get a sense of how to estimate first order partial derivatives off of a graph. And we had kind of an example initially where we could sort of see what that would look like looking at a three-dimensional version of this graph, right? Then this was our first example from this section, that in this case, both the x partial derivative, which was the slope of a tangent line at this point, and also the y partial derivative, which was the slope of a tangent line to the green curve at this point, both of those were positive. We could estimate those using the slopes. But usually having a three-dimensional manipulative like this one is not always what we have to understand a multivariable function. Very often what we start with is something that looks more like this. Right? If I want to know how the altitude in a national park varies as a function of latitude and longitude, very often what we have is a map that looks like this, in which there are little contours drawn on the map that show me where are the areas of equal height. So if I zoom in on this graph as much as I can, oops, oh, that's not what I wanted. I have to sort of read real carefully, but for example, this little contour here is labeled 325, I think. So these are all the points that are 325 feet above sea level, all lie along this contour. And then the next contour in is 350. So all these points are 350 feet above sea level, and so on and so forth. So all these little contours are just what they're doing is that they're labeling the z values, the heights of horizontal cross sections to our graph. So if we were to go back to the function that you were studying earlier today, rather than looking at the x and y traces, what we could have done instead is look at this thing from the top down, and instead of seeing x and y traces, we could ask, what do the contours, or do the horizontal slices of this thing look like? So if I take a horizontal slice out of this graph, the shape that that slice takes really depends on where I'm slicing this graph. So if I slice it directly at z equals 0 along the xy plane, my slice just looks like this, just this line that's drawn down the y-axis. Whereas if I slice it at z equals 1, then the slice that I get is going to have this sort of shape. Right? It has these three different components because I'm slicing it, a little bit higher than the xy plane here. If I slice below the xy plane, I get a slice that has a different shape. It actually only has a single component. And so if I put all of those slices together on a single copy of the xy plane, I'm going to get what's called a contour plot of this three-dimensional surface. So if we took a bunch of horizontal slices of this graph and we just shone a light down on them so that they all went down onto the xy plane, and we looked at it on the xy plane, we would get a contour map, a contour plot of this function. that we should be able to get information about this function from its contour plot. So we should be able to, any question that we could want to use the three-dimensional graph of the surface to answer, we should be able to use the contour plot to shed some light on. So what this final activity in the section asks us to do is to look at a contour plot of a function which we don't know the formula for. So I don't know a formula for this function, but here is its contour plot, and the z values of the contours are labeled over here on the left. So this x-shaped contour here is the value for f of x and y equals 3. So the z value for this function is equal to 3 everywhere along that x shape, 4, 5, and 6, and so forth. And so what the question asks to do is to use this contour plot to estimate some values of the x and y partial derivatives. And I've done that work in your activity stream here to actually do that estimation. Whoops, I'm looking at the wrong one. But what I'm interested in us doing together with your team, so this will wrap up our first partial derivative discussion, is can we use a contour plot to tell us where the x partial derivative is positive, where the x partial derivative is negative, where the y partial derivative is positive, so to be able to just tell the sign, SIGN, of the partial derivatives based on a contour plot. So my recommendation when we do parts D, E, and F are to do parts E and F first, and then save part D for the end. So see if you can use a contour plot to locate one point on the contour graph here where the x partial derivative is negative. So again, think about at what points does increasing x have the effect of decreasing the value of f of x and y. That's what a negative x partial derivative would tell us. And then similarly, find a place where the y partial derivative is positive. So find a place where increasing y will have the effect of increasing f of x and y, the value of the function. So find those 2 points, E and F. And then part D, I think, is the most tricky one. See if you can find a place where increasing the value of x infinitesimally doesn't have any effect on the value of f of x and y. So let's take a few minutes just to look at this contour plot from activity 10.2.6 and find some coordinates of those points. And of course, there could be more than one correct answer on this one. So the idea here, right, is that if we're standing at some point in the xy plane and we increase in the x direction, so if we just walk east on my contour map, if I'm looking for a place where the x partial derivative is negative, I want a place where when I walk east, I'm going to be walking towards the direction of lower contours, contours that have a smaller, lesser value of f of x than from where I started. So if I start at this point over here, it's on the contour f of xy equals 1. So my height, if you like, my elevation is 1 at this point. And if I walk east, if I increase x, I'm walking more in the direction of higher contours, which is 2, than I am in the direction of lower contours, like this one back here at 0. So here the x partial derivative would be positive, because if I walk east, if I increase x, then the output of my function is going to increase, because I'm more walking in the direction of higher contours than I am walking in the direction of lower contours. And the opposite seems to be true down places like here, right? Where if I stand at this point and I walk east, then that east is taking me more in the direction of the lower contour at 4 than it is in the direction of the higher contour at 5. So tomorrow we're going to be able to put the geometry back into this picture and to be able to say, well, what does this sort of walk in the direction thing actually mean? How can we make that a little bit more precise? How can we quantify this notion of, well, if I walk east, am I walking more in the direction of higher contours or more in the direction of lower contours? And how can I use perhaps some kind of an angle to measure, like which direction is going to take me uphill and which direction is going to take me downhill, that kind of thing. But yeah, so if we're looking for a place where the x partial is negative, I'd be looking for a place where increasing x decreases f. Right? And increasing x means walking to the east, decreasing f means walking toward lower contours. And so this would be one example of a place where the x partial is negative. Yeah, I think I'm ready to call the discussion on that one. If we're looking for places where the y partial derivative is positive, we would be looking for places on this contour plot where walking north takes us uphill. So when I increase y, I'll be increasing the value of my function, right? The level of the contour. And conversely, if I walked south, I would be going downhill. Is there a place where walking south takes me downhill on this diagram? I really can't find it. I mean, it looks like this whole thing from northwest to sort of southeast is taking us uphill all the time. And so there's no place at which walking downward is going to be taking me down a hill on this. Well, hold on. Now that I said it that way, well, no, it's kind of hard to say, because in that formulation, you might say, well, what about a point over here? Right. So let's say I have this point. And at this point, if I walk to the south, it's kind of hard to say, but it looks like this actually might be the only place where we can get a legitimate answer. If I walk to the south from this point, it looks like I'm walking more in the direction of this lower contour at 2 than I would be toward in the direction of a higher contour. And we can't see a higher contour anywhere near this point, which is why I think this is maybe not the greatest answer, but I think it's the only answer that would be sort of correct for a problem like this. So there probably is another contour that's higher that we just can't see because it's probably off the picture just a little bit to the top. But yeah, at this point, I think this is probably one of the only places on the diagram where we can convince ourselves that Fy is greater than 0. Because if walking north takes us uphill, that's the same thing as walking south taking us downhill. And there's very few places on this diagram where it would seem that that's actually happening. But this point up here, so 2, 2 or something like that, it's maybe one of the only ways to fill in that blank. So then I asked us to leave this one for last, because I think it's the most interesting in some ways. Can we find a place where the x partial derivative is equal to 0? A place where walking to the east or west, at least infinitesimally, doesn't seem to change my elevation on this contour plot, where it's not clear whether setting off to the east or west would increase or decrease my z value. So if we're looking for a way to walk that does not change our elevation, the one way that we know we can walk without changing our elevation at all is just to walk along one of these contours, right? If I put my toes along the z equals 4 contour and just walk along that curve, then my z value is never going to change. I'm never going to go uphill, I'm not going to go downhill, I'm just going to be walking at a constant elevation.
I think the power the point is constant. You can find it. The power of the function constant.
So if we zoom in on this point right here on the y-axis, then what we're going to see is a contour that is horizontal at that point, right? Because my derivative only sees the first order behavior of my function. So the contour looks like it's horizontal if we zoom in at that point. Which means, infinitesimally speaking, if I walk east or west, the first derivative is not going to be able to tell me whether I'm going uphill or downhill. In order to know whether I'm going uphill or downhill, I would need to either zoom further out, or I would need to use a higher order derivative to tell me the answer to that question. Because the first derivative only cares about slope, basically. It treats everything like it's locally a straight line. And so if I zoom in on this contour, the contour looks like a horizontal line to the first derivative. And therefore, my direction of walking east or west, which also looks like a straight line to the derivative, it doesn't see any difference between those two. And so from the first derivatives perspective, I would just be walking along a contour if I go either east or west from that point. Now, if we had higher order derivatives at our disposal, we'd be able to be a little more specific, because we can certainly see, when we zoom out in the whole picture, that it's not actually true that if I start at this point and I walk east, that I'm not going to be going uphill or downhill, because I can see that I'm actually, if I go east, going to end up at a lower altitude. But again, the first derivative can't tell us that. Right? The first derivative only sees what's happening in a linearized fashion. It only sees the direction of the contour compared to the direction that I'm walking. Right? And so because we're using the word direction so much here, we are presaging what we're going to talk about tomorrow, which is how do we get vectors to the party? How can we use vectors to describe all of these notions of rates of change and to do the kind of work that we were doing in this problem? So what was that? 0, -½ or something like that. To be able to tell if I set off in a certain direction, is my function going to be increasing or decreasing? Notice that in this problem, we were sort of limited to questions about walking east or west, so x partial derivatives, versus walking north or south, y partial derivatives. But once vectors are a part of our life in this process, we'll be able to say, well, what's going to happen if I walk northeast? What's going to happen if I walk south-southwest? What's going to happen if I embark upon, a bearing 271.5 away from where I am right now, right? So once we have vectors in this vector calculus mix, we'll be able to be even more sort of rich in describing how a function changes. What is its output derivative per unit change in its input in any direction that we like. And so what it does is it expands our universe from partial derivatives, which are only in one of the coordinate directions, into what are called directional derivatives. Directional derivatives are derivatives in any direction of change in the xy plane that we wish. And in the process, what we meet tomorrow is a single object. This is another thing that vectors are really good at doing, is packaging together a bunch of different quantities as a single entity called a vector. We're going to meet a single vector object that is going to, for us, represent the derivative, because it's going to contain all information that we could ever need about every directional derivative of a function of several variables will be contained in a single vector. And therefore, that single vector is what we're going to think of as the derivative of a multivariable function. It's called the gradient vector. And so in tomorrow's class, we're going to be introduced to the gradient vector and think about, first of all, what are the interpretations of the gradient vector itself? So what does the direction of the gradient tell me? What does the magnitude of the gradient tell me? And then how do I use the gradient to recover these directional derivatives, to figure out how the output changes per unit change in any direction that I like in the input. So once vectors are here, then that's going to make a lot of these questions much more doable and tractable and give us a lot more flexibility in how we address them.